Good afternoon, everyone. Welcome and thank you for joining this session. Today, I will presenting a comparative review of three leading post-quantum key encapsulation mechanism: crystal Kyber, which is now standardized as a MLKEM, along with BIKE and HQC. This is joint work with my co-authors from Howard University, University of Technology Malaysia, and the University of Suleimania and Sunway University. So, cryptography is in the middle of its biggest transition in 50 years. The public key algorithm that currently secure essentially every TLS handshake, every banking transaction, and every secure messaging app on the planet, RSA, elliptic curve, Diffie-Hellman, are all on borrowed time. Once cryptographically relevant quantum computer arrive, those algorithm breaks. The question is no longer if we migrate to post-quantum cryptography, but to which scheme, and what timeline, and with what trade-offs. Over the next 20 minutes, I will walk you through the quantum threats, the NIST standardization process, the three KEM finalists we focus on, and a head-to-head comparison on key size, ciphertext size, computational performance, and also security guarantees. By the end, you should have a clear sense of which scheme fits with deployment scenario. Let's get started. Okay, let's start with the why. Why are governments, standard bodies, and the entire security industry treating these as urgent when fault-tolerant quantum computers don't actually exist yet at scale? Two algorithms drive these concerns. The first is the Shor algorithm, which is published by the Peter Shor in 1994. Shor showed that sufficiently large quantum computer can factor large integers and compute discrete logarithm in polynomial time. That single result kills RSA, it kills DSA and ECDSA, and also it kills every variant of Diffie-Hellman's. Essentially, the entire public key infrastructure that secures the internet today rests under problems Shor algorithms solve efficiently. The second is the Grover algorithms from 1996, which gives a quadratic speedup for brute force search. The practical effect is that AES 128 drops to roughly 64 bits of quantum security, which is why NIST recommend AES 256 for long-term confidentiality. Now the panel on the right is the part that creates real urgency. We call it harvest now, decrypt later. Adversaries don't need a quantum computer today to attack data. They simply record encrypted traffic and store it. When quantum hardware matures 5 years, 10 years, 20 years from now, they decrypt the archive. So if your data has a confidentiality lifetime longer than the time to quantum computers, your data is already at risk. That's why the migration has to happen now before the threats materialize. Okay, in this slide, we want to track the NIST process, the global standard effort that determines which post-quantum algorithm the world will actually deploy. In 2016, NIST opened a call for proposal. They received 82 submissions covering essentially every promising mathematical foundation: lattices, error correcting, codes, hash function, multivariate, polynomials, and isogenic of elliptic curve. 3 rounds of public cryptanalysis followed. By 2022, NIST announced its round 3 picks. Crystal Kyber was selected as the primary KEM. Dilithium Falcon and SPH INC plus S plus took the digital signature slides. That same year, the isogeny-based candidate Psych was completely broken by Castrix and Decro. A single attack reduced its security to essentially zero. That break is a useful reminder of why diversity matters. In August 2024, Kyber became official as MLKEM under FIPS 203. This is the standard you will find referenced in TLS 1.3 hybrid drafts, in Signal's PQXDH protocol, and in the Chrome's experimental key exchange. So then in March 2025, NIST announced HQC as a backup KEM. The reasoning is on the bottom of this slide. If a future cryptanalytic breakthrough damages lattice-based security, deployment needs an alternative built on entirely different mass. So HQC is a code base. So its security relies on a different hard problems. The draft FIPS standard for HQC is expected in early 2026, with finalization before 2027. So the global picture today is one standard Lattice KEM, one code-based KEM underway, and Bike is still under review. Okay. Before we compare specific schemes, let's quickly nail down what a KEM actually is, because the term is sometimes used loosely. A key encapsulation mechanism is a primitive consisting of three algorithms. Keygen produce a key pair, a public encapsulation key, and a private decapsulation key. Encaps take the public key and produce two outputs simultaneously, a shared secrets and a ciphertext that travels over the wire. Decaps, as you can see here, takes that ciphertext, apply the private key, and recovers the same shared secrets. The shared secrets is what then feeds into a symmetric encryption algorithm, typically AES-GCM or ChaCha20 or Poly 1305. So the KEM's job is just key establishment. The bulk encryption is handled by classical symmetric primitive, which Grover only weakens by half. The security target is IND-CCA2 indistinguishability under adaptive chosen ciphertext attacks. This is the gold standard for the key exchange. Informally, it means an attacker who can adaptively query a decryption oracle still cannot distinguish encapsulated keys from randoms. So all three schemes we will discuss reach IND-CCA2 the same way. They start with an IND-CPA, secure public key encryption primitive, and apply the Fujisaki-Okamoto transform, which essentially binds the ciphertext to the randomness used to create it. For Bike, this is more delicate because of decoding failures. We will revisit that. So for MLKEM and HQC, the FO transform composes cleanly. With this background in place, we can now look at each candidate. So MLKEM is the headline act. It started life as a Crystal Skyboard, a submission to the NIST process by the team including Avanti, Bose, and Dokas, and others. Following round 3, NIST selected it as a primary KEM, and in August 2024, it was published as a FIPS 203 under its official name MLKEM, or Module Lattice-Based Key Encapsulation Mechanism. Its security rests on the module learning with error problem, or MLWE. Module LWE is a structured variant of regives classical learning with error, where instead of working over plain integer lattices, you work over a module that is a vector space over polynomial ring. This structure is what makes MLKEM compact. You can represent vectors of polynomial instead of huge matrices. So keys and ciphertext shrinks, and because the underlying ring has a number theoretic transform, polynomial multiplications run in n log n time, which make the whole scheme fast. So FIPS 203 specifies three parameter sets, 512, 768, and 1024, corresponding to NST security level 135 and 5. Whichever you pick, the output is a 256-bit shared secret, which slots directly into AES 256 or ChaCha20. So in CCA2 security is achieved through the Fujisaki-Okamoto transform applied to an CPA secure public key encryption scheme. This is the most mature, most analyzed, and most deployed of the three. If you need to ship a quantum safe handshake today, this is what you ship. Okay, let's talk about the BIKE or bit flipping key encapsulation. It is the first of our two code-based candidates where MLKEM relies on the lattice problems. BIKE move into completely different mathematical universe, error-correcting codes. So specifically, BIKE is built on quasi-cyclic moderate density parity check code or QC MDPC. Its security reduced to the difficulty of the syndrome decoding for those codes, which is a problem that has resisted attack since Mac Lee's original code-based crypto system in 1978. The bit flipping in the name refers to the decapsulation algorithm, which uses an iterative decoder called black-gray flip. Each iteration tries to identify and flip suspicious bit to correct the introduced error. So this decoder is fast and has low implementation complexity, which is one reason BIKE encapsulation is the fastest of the three at security level 1, only 97 kilocycle, as we will see shortly. So however, BIKE has one significant catch, the coding failure rate. So for IND-CCA2 security via the FO transform, the DFR has to be negligibly small, typically below 2 power of 128 or 2 power of 192. So the BIKE team has provided a strong empirical extrapolations of the DFR, but a formal upper bound proof is still open. So it is an active area of research, and this gap is part of why BIKE remains as a round 4 candidate rather than a finalized standard. So the same NIST report also notes why some weak key classes that have been identified, which adds further uncertainty on the residual security sides. So BIKE is therefore best understood as a strong research candidate with attractive performance and size characteristic, but with a security story that is not yet fully closed. Okay, HQC or Hamming quasi-cyclic is the second code-based scheme and the one NIST ultimately selected for the standardization in March 2024 as a backup of KEM. So like BIKE, HQC security rests on a syndrome decoding problem with quasi-cyclic codes, but in the Hamming metric. So the construction itself is different. Instead of using MDPC codes with an iterative bit flipping decoder, HQC built a public key encryption scheme that internally uses concatenated code and an outer read Mueller code combined with an inner read Solomon code. as illustrated in the diagram on the left you can see here. So that choice may sound like a minor implementation detail, but it has a major consequence. The decoder is mathematically transparent. Coding theory gives you closed form bounds on how often the concatenated decoder will fail. So unlike BIKE, where the DFR is estimated from extensive empirical extrapolations, HQC's DFR has a formal upper bound derived from the structure of the codes themselves. For a scheme that needs INDCCA2 via the FO transform, this is a significant theoretical advantage, and it is single biggest reason NIST selected HQC over BIKE as the backup standards. So the trade-off is bandwidth. HQC ciphertexts are roughly 6 times larger than MLKEMs at the same security level. That's a real cost, but it's the price you pay for cryptographic diversity. If a future cryptanalytic advance against lattices ever materialize, having a deployed code-based fallback ready to go is worth those extra bytes. So draft FIPS standards for HQC is expected in 2026, with finalization targeted before 2027. Okay, now we move into direct comparisons. The first comparison table covers the security side of the trade-off. Look at the second row, you can see family. We have one lattice schemes, MLKEM, and 2 code-based scheme you can see here. So 2 code-based scheme, BIKE and HQC. This is exactly the diversity NIST wanted. Deploying MLKEM and HQC together gives you protection against any single mathematical assumption being broken, even if a future algorithm dramatically reduces the cost of lattice saving, your HQC protected traffic is unaffected, and vice versa. So the INDCCA2 rows is where the scheme starts to diverge in maturity. MLKEM has a clean security proof. CSPA security plus the Fujisaki Okamoto transform delivers INDCCA2. HQC, as you can see here, has the same FO-based reductions, and crucially, its decoding failure rate has a formal upper boundary from the coding theory. So the FO transform preconditions are rigorously satisfied. BIKE also relies on a FO, but its DFR is bounded by empirical exploration rather than a formal proof. That's what the DFR dependent annotation means. BIKE's INDCCA2 claims is conditional on extrapolated decoding behavior holding at cryptographically relevant parameter size. So the best known quantum attack, RAW, as you can see here, is reassuring across the board. Lattice sieving and information set decoding both run in exponential time. This is no Shor style polynomial time attack against any of these. So the bottom row tells the deployment story. MLKEM is shipped. HQC is selected, but and on the way. BIKE is still under review. The key takeaway summarized in the bar bottom you can see here. So 3 different hard problems give us defense in depth. In this diagram, we are talking about the bandwidth picture. So the chart shows that the public key size in dark cyan and ciphertext size in amber. For both NIST level 1, the left 3 bars, so you can see, is and level 3, the right 3. So start at the bottom left. MLKEM 512, you can see here, an 800 byte public key, a 768 byte ciphertext. Total wire overhead of just over 1.5 kilobytes. This is genuinely small enough to fit comfortably inside a single TLS handshake without restructuring. It is also dramatically better than where many of us feared post-quantum bandwidth would land. And byte L1 sits in the middle, about 1.5 kilobytes public key, 1.5 kilobytes ciphertext, total around 3.1 kilobytes, roughly double MLKEM, but still very manageable for most applications. But HQC128 is where you start to feel the cost of code-based diversity. Its public key is 2,249 bytes, comparable to byte, but the ciphertext jumped to 4,497 bytes, as the panel on the right notes. That's about 5.9 times larger than the MLQM 512 ciphertext. Move to level 3, and the gap widened further. HQC 192, as you can see here, needs a 9042 byte ciphertext. MLKM 76 needs only 1088, almost an order of magnitude. Why does this matter in practice? In data centers and desktop scenarios, the difference is invisible. But in IoT networks, satellite links, constrained radio protocol, and high-frequency TLS shakes, kilobytes matters. So every additional handshake byte translates into latency, battery drain, or a spectrum cost. This is the central trade-off you accept when you choose HQC for diversity over MLKEM for compactness. Now performance. This chart shows kilocycles. Fewer is better for the 3-core operation on a modern x86 64-bit processor and NIST level 1, drawn from the NIST 5th PQC conference panel in April 2024. So MLKEM and HQC are running on AVX2. Byte is running on AVX512. So look at MLKEM first. The dark cyan, you can group key gen 1 through key gen 123 kilocycle, encaps 155, and decaps 289, as you can see here. Total around 567. Most importantly, the 3 operations are balanced. There is no single bottleneck. That balance is what makes MLKEM such a good general purpose choice. Byte in the middle, as you can see, has a streaking shape. Its encaps is the fastest of the 3 at just 97 kilocycle. You can see. That's the headline wins for byte, but keygen jumped to 589 and decaps jumped to 1135 kilocycle. That decaps cost is the iterative bit flip decoder doing its works. So byte is excellent if your workload is encapsulation heavy and you can amortize key generation. But it's less attractive when decapsulation latency matters. But HQC on the right has a different profile again. Keygen is actually the fastest of all 3, only 87 kilocycle. That makes HQC interesting for protocols that regenerate key frequently or use ephemeral keys. Encaps is slower. Encaps as the GAMs come 204 and 362 slower than MLKEM, but within practical bound. So the headline, MLKEM is the most balanced. Byte wins on encapsulation only, and HQC wins on key generation. Total throughput at level 1. MLKEM 567, HQC 653, and byte 1821. So MLKEM is more than 3 times faster end-to-end than byte, and that gap actually widens on level 3. So putting all of this together into deployment guidance, which is really the question most practitioners care about. Part 1, MLKEM is the deploy now choice. It is standardized under FIPS 203 and it has the most mature implementation ecosystems. And it is already being rolled out in production. So TLS 1.3 hybrid draft use it. Signal's PQXDH protocol use it. Chrome's hybrid key exchange is X25519 plus MLKEM. If you have a project that needs quantum safe key exchange in 2025 or 2026, this is the answer. So card 2, so we have HQC, is the plan for choice. It's not for replacing MLKEM. It's the backup. The deployment scenarios where HQC matters are systems where the data has a very long confidentiality lifetime, or where regulators require cryptographic diversity, or where the cost of the future lattice breaks would be catastrophic. So government archives, defense system, long life medical records, and so on. So HQC draft FIPS standard is expected around 2026 and with finalization before 2027. So the most teams, this is a 12 to 24 months planning horizon. So card 3 bike, as you can see, is the watch and evaluate choice. Its real strength is small ciphertext, fast encapsulation, but the open DFR proof and the weak key class concerns means it is not ready to be deployed broadly. It's a good candidate for research, for niche application with the right workload shape and for tracking as it matures. Finally, the dark bar, as you can see here at the bottom, talking about the hybridization. During this transition, the consensus best practice is to run a post-quantum KEM in parallel with a battle-tested classical algorithm. MEKEM combined with X25519 is the canonical example. You are quantum safe if either component holds, and you don't bet your security on a single new assumption. Okay, let me close with 3 takeaways and the open work ahead. First takeaway, MLKEM leads on size and speed. The smallest key of any candidate balance operation costs across keygen, encaps, and decaps, and a fully published FIPS standards, FIPS 203 standard as of the August 2024. If you only remember one scheme from this stack, this is the one to remember as your immediate quantum safe default. Second one, HQC is the formal DFR backup. So its code-based foundation and rigorously bounded decoding failure rate are exactly why NIST chose it in March 2025. Run it alongside MLKEM is a long life or high assurance system, and you are hedged against a future lattice break. And third key takeaway is Bike. Bike remains a strong research candidate, genuinely compelling encapsulation performance and ciphertext size, but the open DRF proof and identified weak key classes means it's not ready for broad deployment. Worth tracking, worth researching, and not yet worth betting on. So the future work bar at the bottom, so you can see here, captures the open engineering challenges, building constant time implementation that survive on memory constrained microcontrollers, hardening implementation against side channel leakage, power, timing, and electromagnetic, and also harmonizing hybrid post-quantum plus classical protocol design across the IETF, NIST, and other standards bodies. None of these is solved yet, and all of it is essential before we can declare the migration completed. Thank you very much for your attention, and I'm very happy to take any question you have about the schemes themselves, about the comparison, about the deployment, or about where this field is heading next. Thank you very much.